Welcome. In this section, we're going to begin talking about transformations. And the basic idea here is that we have all of these different functions, these really different basic functions. So you can see here I've got 7 pictures. And we want to think about these as being parent functions. So parents make children, and the children look like the parents, but are a little bit different. In this case, we're going to think about that parent function as being the just most basic version of each type of function. So we have one parent, and the idea is that we'll add all of these different numbers to the function, and just by looking at it, we'll be able to determine what the function actually looks like. So we have a good idea in our head without having to pull out our graphing calculator. First things first, we want to make sure that we understand what these different types of parent functions are. Okay, so these are our parents here. So the first is the identity function, and the identity function is the most basic linear function we could come up with, which is just y equals x. The second one is a squaring function, or quadratic, which we learn a little bit more about later. But quadratic functions have this parabolic shape. They're shaped like a U. We have square root functions such as y equals the square root of x, and our square root function is basically half of that parabola turned on its side. Cubic or cubing functions, these are kind of a snake function going up and down. Those could be written as y equals x cubed. Whereas a cube root is that same snaky shape. I know they all look like snakes, but horizontally. So y equals the cube root of x. We can have a reciprocal or a rational function, which would be where the x is in the denominator, such as y equals 1 over x, as well as absolute value, y equals the absolute value of x. And these are not the only parent functions. We could also talk about logarithmic or exponential, but we really don't touch on those until the end of the semester. All right, and there are trig functions. So when you move to trig, all of these transformation ideas and concepts, they're going to transfer over to sine and cosine and tangent graphs. All right, so continuing along, just making sure we understand what we would be doing here. We're going to create new functions, right? New shaped graphs by shifting. We can shift horizontally, which would be left and right, or vertically would be up and down. We could stretch, so we could pull things vertically, or we could stretch things out horizontally, versus shrinking, smushing things in on each other, right? So thinking about shrinking in. And then we can deal with reflections, so flipping them over either an x or a y axis. The main idea, again, we're going to be adding some constant. When I say constant, I'm just meaning a number. So we're going to add a number to a function. And when we add that number, we're going to want to consider 3 things: location, operation, and then the sign. And we're going to talk about how the location and the operation and the sign give us these clues so that we know how adding each of these different values changes the shape of the graph. So let's expand more on those 3 concepts: location, operation, and sign. Considering just the location lets us know if the value affects x and creates a horizontal change, or it affects y. So thinking about this, when something affects y, that means it's a vertical change. Up and down is where the y-axis is. And when things affect y, we locate them as being outside of the grouping mechanism. Versus if we consider x, or something being horizontal, it's going to be inside the grouping mechanism. So the the really important thing to remember here is that when things affect y, right, when you have a number added to this function and we know it's affecting y, it's going to behave exactly as we would expect, right? So if it's +3, that would maybe mean up 3. Whereas if it is -2, that would mean we'd shift down 2. Consequently, when we are dealing with horizontal, it's always going to do the opposite of what we think. So location, what we think about here is that vertical is on the outside, it's good, it's free, whereas horizontal, those are things that are on the inside, maybe inside bars being that grouping mechanism. Think about behind bars. Because you are bad, you don't do what you're supposed to do. You do the opposite. So that's kind of my mnemonic device. All right. Outside, you're good, you're free, you're going to behave as we expect. That means you affect Y. Inside the bars is going to mean you do the opposite of what we think you're going to do and you behave badly. All right. So we've got location. Then we have operation. So the operation, we have two essential operations in math. We have adding, small parentheses, or subtracting, and then we have multiplying, or small parentheses, division. So we have addition or multiplication. If something is added, that means we are going to shift. That means we're going to pick the function up and move it up, down, left, right. Whereas if it is multiplied, that's going to imply a shrink or stretch, as well as the potential to flip. Okay, so addition means shift. Multiplying means stretching or shrinking, and or a flip. And then the last thing we want to think about is the sign. So the sign, are we dealing with positive versus negative? Positive makes sense. If it's positive, then we would go up, we would go right, or we would have no flip. And then negative would go down, left, or yes, we would flip or reflect across an axis. All right, and the last piece here is if we multiply by a negative, when we talk about that flip, that always causes a flip. And a horizontal flip, flipping horizontally, that means we would travel across the y-axis. Whereas a vertical flip, flipping up and down, that would be traveling across that x-axis. All right, so these are the three things we want to think about: location, operation, and sign. And now I'm going to embarrass myself with song. Tell me the location, let's focus on the operation, 'cause I just need the sign and space to make moves. So I'm sure you guys have all heard that song. I know it's a little dated now, but it's still good. And Location by Khalid. And it'll help you maybe remember what you need. So you need location, operation, and the sign. And just keep in mind, if we had been in class, you'd have gotten to see me dance with that too. Hopefully one day in the future. All right, so let's summarize this in a box. All right, so another way to help us remember these rules without talking about them formally, and we'll address that in the next video, but these are kind of my like mnemonic devices. So we think about the location, tell me the location, and the operation. So we've got operation and location. So we're looking at inside versus outside, adding versus multiplying. So thinking back, what does outside mean? Outside lets us know it is going to be a vertical change. Versus inside lets us know we will be having a horizontal change. And the main thing we want to remember is that outside, good, behaves the way you expect. Inside, thinking about that like being in jail, it's always going to do the opposite of what it looks like. So it's a shady little number. Now, if we are adding, that means we will have a shift. So a vertical shift would be plus k up or minus k down. So vertical shift, we're dealing with up or down. Whereas a horizontal shift, if we have plus h or minus h. So plus h, that would actually go to the left, and minus h would go to the right, because you'd think horizontally, we'd move left or right, and it's going to be opposite of what you think. So we've got left or right. Now, the H and the K that I'm using here, these just represent the variables that we use in our definitions when we're describing this. So we'll talk about HK, and then in a second here we have A and B as well. We'll talk about those when we get to the formal definition. And then if we are multiplying, so multiplying implies a shrink or a stretch. So a vertical shrink, so vertically shrinking would be compressing on itself versus vertically stretching would be getting larger. So shrink or stretch. And if it is negative, that means we would have a vertical flip across the x-axis. So we'll have a reflection across the x-axis. So we would be multiplying or dividing the value we use here. We call this A in our definition. So multiplying or dividing by an A. And then a horizontal shrink or stretch. And that would mean we would be compressing in horizontally or stretching out vertically. And of course, if this is negative, we're going to have a horizontal reflection, so that would be across the y-axis. And the letter we use here is C. So we're going to talk about, I know this video is getting a little bit long, but we're going to talk about this A and C value as well as K and H. Here you can see our more formal definitions the way you would see in the text. And essentially you see we have some function y equals f of x. And in all of these situations, here we have a times a or a times c, a plus k and a minus h. All right, so a, c, h, and k, those same values coming into play, a, c, h, and k. So A multiplied on the outside. When we deal with multiplication on the outside of some grouping mechanism, well, if it is a positive number that we are multiplying by, there will be no flip. But if we're multiplying by a negative number, then we will flip over the x-axis. So positive and negative, all those have to do with when we're multiplying is they tell us whether or not the graph flips. Now, if the absolute value, disregarding the negative portion, if the absolute value is greater than 1, bigger than 1, you'd think something is going to get bigger. So we will stretch vertically or in a sense get taller. But if that A value, the absolute value of A, again, disregarding the negative, if that's between 0 and 1 or fractional, we're going to have a graph that shrinks down, compresses vertically. And here you'll notice A is multiplied times f of x, which means y. So in a conceptual setting, if we were trying to transform a point or an ordered pair, we would take the y value and just multiply it by A. Looking here at the next one, dealing with C, you'll notice that the C value is multiplied inside the grouping mechanism with X. So this means we know it is going to affect X. We also know when things are horizontal that it's going to behave the opposite of the way we think. So we think, hey, this number is in the bars with X. X is bad. It's always going to do the opposite. And so the only thing that doesn't go along with that is the flipping. So if we multiply by a positive, there's no flip. If we multiply by a negative, the graph reflects across that y-axis. Now this is where the opposite comes into play. So if this number we are multiplying by, the absolute value of it, if it is greater than 1, you'd think bigger than 1 would get bigger, but it actually shrinks. And if it's fractional, you think about, cutting something in half, fractional between 0 and 1, it would actually stretch. And so we use the opposite operation when we apply C to that X value in a point, we would actually be dividing. We're using that inverse operation. Now we'll talk about K, our vertical translation. Notice K is added and it's on the outside of the grouping mechanism. If you add a positive number, the graph moves up K units. If you add a negative number, the entire graph shifts down K units. So you would be adding or subtracting K to the Y value in any ordered pair. And then the last letter that we talk about here is H. And notice H is added. Remember, adding is the same as subtracting. H is added on the inside. So adding on the inside, that's a horizontal shift, means we'll shift left and right. And you'll notice that the standard form here has a minus inside. There's a minus in front of H in the standard form. This is going to cause us to do the opposite. So this is where really you can kind of see why it would be opposite. And this is why, because if you had positive and you tried to write positive with a negative, you would need to use two negative values. That would be like saying minus negative H. So again, if H is positive, that would mean shift right. And if H is negative, that means we're going to shift left. However, it doesn't look like that. So if I had f of x minus 3, x minus 3, that would mean H is positive 3. Even though this looks like a minus, H would be positive 3 because of that standard form. So this would actually indicate we would move right 3 units. So whatever you determine the H value is, that's the opposite of what it looks like, you would actually end up subtracting that from your X. And I've got two little examples here. You can pause and look at that. We're going to really focus on some examples in the next video. All right, so this is really just about understanding the rules. And at this point, I've essentially said the rules, these 4 basic rules 3 different ways. So one last thing before we move on to the examples in the next video. I'd just like to show you some examples of what these transformations, the A, C, H, and K values, might look like in different types of functions. So linear, quadratic, absolute value, square root, cubic, the list goes on. We have rational, exponential, and logarithmic. We don't get to that until much later in the semester. But what I want you to notice is we have an A value multiplied on the outside here. So all of these A's, this is a number times some expression on the outside. And the K's, we are adding K. Notice all of those values are on the outside. And then if we look at what is inside the grouping mechanism with X in the absolute value bars, under the square root, in the parentheses, in the denominator, you'll notice we have C times X minus H. C times X minus H. C times X minus H. So the purpose of me showing you this screen is to just help you see that patterning and how we like to organize things when we're trying to determine what is going on inside these problems. All right, so that's going to conclude this video. I hope you got all of those notes down because now we're going to go to the next video and we will apply them.